Hi, everybody, and welcome to a presentation on how to determine thermodynamic properties of substances that can change phase. And these would be things like H2O. You well know it's probably the best example because you're familiar with water and steam in the kitchen, boiling water, but also things like propane that can change phase. Propane that you use for fuel, but you buy it in a tank as liquid. Things like refrigerant, typically R134A, that's just a brand of refrigerant that we use in our air conditioners throughout our lives, refrigerators, air conditioning in automobiles and in our home. So here we go. Let's see if I can help you get a physical feel for how to identify the phases of those substances, as well as getting thermodynamic properties for those substances, because your homework is involving those, and all of your subsequent homework, most all of your subsequent homework problems are going to involve the evaluation of thermodynamic properties like density, specific volume, internal energy, enthalpy. So here we go. All right, I've posted the static PowerPoint file out on the tutoring folder under PowerPoint prep for video if you wish to see these slides in a static way. How to evaluate thermodynamic properties. And I've shown some phase change example substances. All right. And so typically I'm going to have three examples that I'm going to give you. I'm going to work you through step by step for three different examples. And so a typical example is I need to determine the specific internal energy for a phase change substance like H2O. That's what we use our examples, propane, refrigerant. And typically students absolutely have a hard time getting started. This is a tough topic. I don't know what table to use, or I don't know how to start. All right, well, let's get started and see if I can give you some tips on how to get started and learn what table do I use. Here's your starting point. So I must insist, this is where you start every time. Start by drawing with pencil and paper, or however you do your work, a pressure specific volume vapor dome. So this is a to scale version of what a pressure volume PV diagram vapor dome looks like for H2O. Specific volume, remember the units of specific volume, cubic meters per kilogram or cubic feet per pound mass. Let's start. Draw that down. The next thing is remind yourself in your mind, you don't need to write these little words and labels on your PV diagram, but in your mind, you need to remember what phase you're in, depending on where your state is on the pressure specific volume diagram graph, okay, relative to the dome. Okay, so let's see, underneath the dome, you're a saturated two-phase mixture. It's a mixture of, let's say, H2O, water, saturated liquid water, and saturated liquid vapor if you're under the dome. If you're on the dome, if you're laying on the dome on the right-hand side, you're a saturated vapor. You couldn't see that with your eyes, but you'd be a saturated vapor. If you're laying on the left-hand side of the vapor dome, you're a saturated liquid. At least that's what you can see with your eyes. It's liquid that's right at the boiling point temperature. It would be like really, really, really hot water. Okay. If you're to the left of the vapor dome, then you're a compressed liquid. And examples of that would be like tap water, shower water, warm water, boiler feed water. Those would be examples of compressed liquids. You can see all of those things with your eyes, of course. All right, that's going to be key in getting the assignment. What is the specific internal energy of your state, wherever you sit? Okay, So here's a tried and true recipe for getting properties of phase change substances. You're given two thermodynamic properties that have to be independent properties, two of pressure, temperature, specific volume, specific internal energy, enthalpy, and there can be a couple of others. And so, for example, in our problems, we're going to say, well, what is U? What is little u? What is the specific internal energy or any other desired property? We're going to focus on what's U for examples. Okay, here's your recipe. Draw a generic PV diagram with the dome. Draw in a single isotherm line on that PV diagram, a line of constant temperature. Next, depending on what you're given, you're either going to use the pressure table or the temperature table, depending on the properties that you're given, okay? Then you're going to go in and you're going to, the next step is determining the phase of the substance. You're not going to jump right into a table to look up U. You've got to determine the phase. Then, finally, you're going to use the appropriate property table for that property lookup. That's your recipe. So if you didn't scratch this down on paper, remember the static PowerPoint is available out on Jay's Toolbox Canvas site. Okay, example one. This would be a lot like a homework problem, could be a quiz problem. It won't be a test problem because this would be part of a test problem of a much larger, more complex test problem. Certainly could be a quiz question. For H2O, determine the specific internal energy, little u. For pressure is 150 kPa and temperature is 280 degrees C. This is a simple problem. It's tough if you don't know where to start. So here we go. Let's draw, we're going to, step one, draw a PV vapor dome, PV diagram, vapor dome, and a line of constant temperature. You got to commit this to memory. What is a line of constant temperature in isotherm? What does that look like? It starts out high for low specific volume and it swoops down until it intersects the dome. Then it goes across horizontal because it's boiling water, for example. Okay. Then when it strikes the right-hand side, saturated vapor, then it continues to swoop down sort of around the slope of the dome itself. So it's sort of a slow downward slope for superheated vapor. That's what a line of constant temperature looks like. Just draw that in. Just draw that in. You got to have that. The next thing we do for our example problem, we're given pressure and temperature. So most students say, well, which do I use? Do I go to a pressure table or do I go to a temperature table? The answer is you can use either one. For this problem, I have personally found it easier to use the pressure table. I have found it when you're given one of your properties as pressure, use the pressure table. That's my personal opinion. So here we are, pressure table for saturated water. Now let's look at our column headings, pressure and temperature. This temperature, the second column, that's going to be the boiling point, also known as the saturation temperature for each of these pressures. Okay, let's circle where we're at. 150 kPa, that's 1.5 bars. You got to remember that. 100 kPa is 1 bar. So we're at 1.5 bars. Okay, we need to look for a number here. The boiling point for 150 kPa is 111.4 degrees C. Jot that down. You're going to write that down on your PV diagram. Here we go. So you're going to label that isotherm that you drew with 111.4. So all temperatures on this line are 111.4. You're also going to label your pressure 150 kPa. So you're getting somewhere on your sketch. Okay. It's kind of like pre-work. All right. The next thing we do is, well, what's our homework problem? We're interested in finding what is the phase for P equals 150 kPa and T is 280 degrees C. Well, at least we know that our point, our dot, our state is going to be somewhere along this horizontal line. But where's it going to be? The next thing we do is we draw in your isotherm line, our isotherm line, 280 degrees C. Where will that be? Well, it's going to be one of these dogleg lines that looks a lot like 111.4, and it's going to have to be above it. So a little studying shows your temperature lines are increasing. Isotherms increase going up, decrease going down. All right, so okay, let's draw that in. Great, we're almost there. Chances are good you're seeing the answer of what is the phase already before we go to the next slide, I hope. Okay, our pressure is 150. We've got to be along this horizontal line. Our temperature is 280. We have to be on this isotherm. So the intersection point is right there. Right. What's our conclusion? Conclusion is the phase for H2O at 150 kPa and 280 degrees C is superheated vapor. Okay, don't get lost in the weeds. What are we trying to do? We're trying to find U for this property pair. All right, so we're getting there. Okay, we discovered the phase was superheated vapor. We now go to the superheated vapor tables and we shop around for a table that corresponds to 150 kPa. There it is, 1.5 bar. We shop around for our temperature, 280 C. Oh, here we go. We circled U. The specific internal energy is 2778.6 kilojoules per kilogram. And so I hope you got it. So some folks will say that was just so obvious. I got to tell you, when I was a student, it wasn't just so obvious to me. I had to really study on this. I had to do a number of repetitive problems to teach myself how to do this. Let's recap where we are in the example, then we'll go to example 2. We were given this homework problem, find U for 150 kPa and 280 C. That, in other words, these were independent properties. We verified that they were two independent properties going to our saturation table because we saw that the temperature did not equal the boiling point at our given pressure. That's how we knew we had two independent properties. Okay. So then we discovered through little plotting work, pencil and paper, that the phase is superheated vapor. That's what enabled us to go to the superheated vapor property table to look up U and get our number. So, so many students will get on a call or in the classroom say, what table do I use? Gee, professor or instructor, what table do I use? If that professor or instructor says, we'll use the superheated tables, but they're not doing you any favors. The trick is learning, how do you get to the superheated tables? Why do you use the superheated tables? And the answer is, you got to do a little pre-work on your own. Okay? I hope that helped. Let's go to example 2. It's going to look very familiar, very similar. Determine the specific internal energy, U, for H2O at 200 kPa and 90 degrees C. So we've got a different pressure and a different temperature than example 1. We're going to repeat our process. Draw the vapor dome with a single isotherm line. That's our starting point. We're given P and T. So I find it's easiest to use the pressure table. So let's go to our pressure table. And here's 200 kPa is 2 bar. What's the boiling point? 120.2. We'll label that on our PV diagram isotherm. We're at 200 kPa pressure. We're at 120.2 degrees C. So on this isotherm line, all temperatures are 120.2. Where do we fit? Where does our temperature fit relative to this isotherm line? I hope you're catching on. Okay. Well, 90 degrees is less than 114. So let's draw in an isotherm line below the boiling point. Okay. We just drew it in. Now, can we see where we landed? Where did we land? Where's our intersection point between temperature and pressure? There it is. Okay. It's going to have to lay on this horizontal line for pressure, and it's going to have to lay on this temperature line for temperature. There it is. What is it? What's the phase? Compressed liquid. There it is. Great. Okay, so now that's what's it. No, superheated tables? Absolutely not. We don't go to the superheated tables. We don't go to the saturated tables. We go to the compressed liquid tables, and here it is. So we turn in our books, we find compressed liquid water, and we look and we think we're almost there, and the first thing tabulated, the lowest pressure tabulated for compressed liquid water is 25 bars, and look, we're at 2 bars. We couldn't possibly use this table. It's the wrong pressure. Okay, what do we do? And looking at higher pressure is not going to do us any good. We need a lower pressure, and the book's not giving it to us. What the hell are we going to do? We got to go back and read our textbook. So I'm not going to force you to do that. I'm going to give you a screenshot. It will pay you, though, to go back and read section 310 in your textbook. And 310 says properties of liquids, compressed liquids. That's what we're interested in doing, compressed liquids. Okay. And in the text, it reads that, says, look, for things like tap water, it turns out that tap water is basically an incompressible substance. You can't make tap water smaller, no matter how much pressure you exert on it. It's true. We engineers treat it as tap water as an incompressible liquid. Okay, easy to remember that. Functionally, what do we do? Functionally, what does that mean? I'm going to go to the next slide to show. Here's some equations. It says the internal energy for any temperature and pressure for a compressed liquid is about equal to, see that squiggly equals, about equal to U sub F at the temperature of the liquid. That's exactly what we're going to use. And I'm going to try to drive it home. I've got another slide in bigger font. Okay, here we go. For a compressed liquid phase. And so as a reminder, here's where we're at in the here's our phase, this yellow shaded area. There's our phase, compressed liquid. Evaluate thermodynamic properties, specific volume, density, internal energy, enthalpy, and S, whatever S is, okay, at the temperature of the compressed liquid substance. So I've written it out again to try to drive it home. U is equal to UF evaluated at your temperature, Okay, back to our example problem. Okay, so with all that little sort of mini lecture, back to our example problem, we're seeking to find the internal energy U, 200 degrees, 200 kPa, 90 degrees C. Well, what we're gonna do is gonna go to the temperature table for saturated liquid. Okay, we're gonna look up our temperature at 90, and then we're gonna look up U sub F at our temperature is 376.85, and there's our answer. The internal energy for water at 200 kPa and 90 degrees C, compressed liquid, is 376.85 kilojoules per kilogram. There's our example. All right, let's recap. For this example, we verified that we had 2 independent properties, P and T, because the temperature did not exactly equal the boiling point at our pressure. Okay. We discovered that our phase was compressed liquid. Okay. Then we got a barrier. We couldn't look in compressed liquid tables to get U. Our pressure was too low. So we had to refresh our memory for section 310 in the text. Okay, and the rule, the engineering approach for us engineers is to evaluate U at U sub F, the specific internal energy of saturated liquid at the temperature of the fluid. So that's how we got 376.85. If anybody were on the call, I'd say any questions, but there's nobody on the call here. A third example, slightly different, but similar. Determine the specific internal energy U for H2O for 200 degrees C given temperature and specific volume is some number, is 0.1 cubic meters per kilogram. See how this is different? Not pressure and temperature, but temperature and another property. This property pair is independent. These are two independent properties, no matter what. T and V are independent properties of each other. So that's great. We're going to start at our usual starting point. Here's our problem statement. We're going to draw another PV diagram with a single isotherm line. Always start with that. The next thing we need, let's plan our work. So remember, we don't know what the pressure is. So we're not going to know what to label this value, okay? But what we're going to do is we're going to go to our saturation table and we're going to write down what is V sub G and what is V sub F. That's our next step. Here it is. Okay. So we're going to label our isotherm lines with values for specific volume V. So let's go to, we're going to use the temperature table because that's what we're given. We're going to go down to a temperature of 200 degrees C, and we're going to write down two numbers. Here's our two numbers, V sub F and V sub G. Let me really point out, look at this column heading, saturated liquid V sub F times 10 cubed. So what that means is this number 1.1565 is actually, so on your paper or on your graph, the specific volume of saturated liquid V sub F is 0.0011565. Be very aware of that, student. Very tricky in SI units. Be very careful of that trick. Much easier for V sub G. We just write down. Notice the column headings. We just write down it's 0.1274 meters cubed per kilogram. Okay. Very aware of that. It can really trip students up on quizzes, tests, and engineering problems in general. This times 10, 3. You got to move the decimal point 3 points to the left is what V sub F is. All right. So now we're back to our problem. I've got to move my Zoom bar up. Excuse me just a second. I'm moving my Zoom bar up on my screen. Okay. Here's our labels. 0.1274 V sub G, 0.0011565 V sub F. Now, we're going to go to the next slide, but can you see where does our point land on this PV diagram? 0.1. It's easy, but we're going to be right around there. We're to the left of 0.1274. There we are. But on your graph, you're going to just maybe make a circle where you're at. Okay. And we got to find the specific internal energy. What we did here is we discovered that the phase of our state is a saturated mixture. So there's some additional steps we got to do. Here's what we're going to do for the next steps. We've got to find the quality X. We've got to find our quality X. And once we have X, the quality, some number between 0 and 1, some number between 0% and 100%, once we find that quality, then we'll do the math to determine U. So let's continue on. Work on what's the quality. Here's what I want you to do. Okay, so this is worth some discussion. The quality visually, so here's the equation. So some students will say, I'm going to go to the book and I'm going to write down an equation for X. So you can find this formula in your book. X is the quantity V minus VF divided by the quantity VG minus EF. That is a formula. However, I admire students who say, I have trouble, I do better visualizing things rather than memorizing formulas. I like that approach. I congratulate that approach. So here's the visualization of quality. The visualization is a proportion, a ratio of this with your eyes. Look at that. Visualize that distance right there. Let's call that Z1. And then visualize your eyes, this distance from here to here. That's Z2. And so without even memorizing a formula, the quality X is a ratio or a proportion. It's simply the distance Z1 divided by the distance Z2 from your work that you're looking at with your pencil and paper. So you don't even have to go to the textbook to write down the formula. It's my hope that you can see with your eyes that here's the numerics of finding the quality. 0.1 minus that tiny number, 0.0011565, divided by the quantity, 0.1274, minus that tiny number, 0.0011565. Okay, so without even looking at the formula, you should be able to get the numerics done to find that the quality of the saturated mixture of our little problem is 78.3%. Okay, we're not there yet. We haven't done our answer. We're looking for you. We just found the quality. Next step. Okay. Also, so we're still in the temperature table. We could have written a couple of numbers down while we were writing other numbers down. That's typically what you're going to do is you're going to plan ahead the big picture and write down U sub F 850.65 and UG 2595.3. You'll write those down, okay? And then you'll do the math. You're going to go back to the definition of quality, apply the math, and get your answer. Here we go. X was 0.783. We wrote these two numbers down from our temperature table. You are certainly welcome to find in your textbook a formula. Here's a formula, okay? You can apply that formula, or you can kind of remember, what does quality mean? It says that, look, quality is a proportion of vapor in a mixture divided by the total mass. So it's easy for me to remember that the internal energy U is that proportion times U sub G, the saturated vapor part, plus the proportion that's left over, 1 minus X, okay? Like if this were 80, let's say this were 80 instead of 78%, it would be 80%, okay? Plus whatever's left, it's kind of like around 20% times UF. So this is one of those situations where certainly you can memorize a formula, or you can do this enough that you can kind of get it in your mind without memorizing the formula. Either way is good. Whatever brings on success for you personally. Okay, I was one of those visual type people, had trouble memorizing formulas. I was terrible at memorizing formulas. Some of my classmates were excellent at memorizing formulas. So it's a very personal thing. It's really up to you to decide how you want to self-teach yourself to become a practicing engineer. All right, here we go. Let's recap for example 3. We had a temperature-specific volume pair. Those are two independent properties. So we looked up VF and VG to observe that for this problem, we are a saturated mixture. So we wrote those down, VF and VG. And so we use those along with our value of V to determine X, the quality, okay? Then we went and we looked up UF and UG. Then we used the quality and those two values of UF and UG to determine U, and we got a numerical answer, 2216.6. Okay, that's example 3. All right. Woo! So we've just about made it through the video. A quick recap of what do all 3 of these examples have in common? What did you learn from each example that were similarities? Okay, let's see what we've got. Okay, you need to start with 2 independent properties. T and V are always independent. P and V are always independent. P and H, enthalpy, always independent. And there are many other, there are many other combinations of property pairs that are independent. However, pressure and temperature are only sometimes independent properties. They are dependent properties whenever one of these is at the saturation condition of the other, whenever it's at the boiling point. All right. Always start with a PV diagram. Always draw a single isotherm line. Use that tool to identify your phase. Okay. So for example, when we had this TV combination, we had to look up VG and VF to determine the quality and observe that it was a saturated mixture. Otherwise, it's either a superheated vapor on the right or a compressed liquid on the left. And so then you're going to use the appropriate property table depending on the phase. And don't forget that trick about compressed liquids. So that is it. I need to successfully stop recording and hope that this really helped you in terms of identifying phases of phase change substances and then getting the thermodynamic properties like U, specific volume V, enthalpy H, and there'll be others as we go along. Okay, hope to see you again soon.